Carbocation rearrangements. These can be kind of tricky to figure out what's happening. Typically, you'll need to know if you had a carbocation rearrangement is if somehow the sigma bonds change. What I mean by that is, like in this first example, here the alpha carbon is secondary, and we're changing this Br into an OH, so we're dealing with some type of substitution. But the alpha carbon on the right is tertiary. Going from a secondary alpha carbon to a tertiary alpha carbon is somewhat changing the arrangement of the different atoms. So this is probably when you see this, a rearrangement has taken place. And rearrangements occur when you're dealing with carbocations. So oftentimes you'll see them in SN1 and E1 conditions. So, in fact, we see that right here. We have a secondary center, and our nucleophile is an SN1 nucleophile. In the SN1 reaction, you have the leaving group leave, giving us a secondary carbocation. Now, secondary carbocations are actually pretty slow to form and are also pretty darn reactive when they are formed. And so most of the time, the bromine will just add right back on. So bromine comes on, comes off, comes on, comes off. It's trying to wait for this water to arrive. But secondary carbocations are very reactive, and so they're not very stable. And before the water has a chance to attack, what can happen is you can shift a group from a neighboring beta carbon over to that carbocation. And this group can be about anything, hydrogen, carbon, about any group that you like. The caveat is there must be some driving force to this. Like here we have a secondary carbocation. If I shift this hydrogen over, get a tertiary carbocation. Tertiary carbocation is less likely to go back to the secondary carbocation because the tertiary carbocation is more stable. The driving force in this reaction is you're going from a secondary carbocation to a more stable tertiary carbocation. And this is what water adds to. And to finish up the mechanism, and have water take that proton off. We have given it the product. Another type rearrangement happens here. Again, the carbon skeleton has changed. Here, this OH is on a secondary, it's on a tertiary position. This OH is on a tertiary position. But now we have quaternary carbons, carbons bonded to 4 carbons as opposed to carbons bonded to only 3 carbons. So, well, a rearrangement has taken place. We've essentially moved a methyl group from one side over to the other side. The way we do that is first we have to form a carbocation. In order to do that, we need to have a good leaving group. That's where the sulfuric acid comes in. It can protonate the OH form the good leaving group leaves. And you get a tertiary carbocation. Now, tertiary carbocations themselves are typically quite stable things as far as carbocations can go. But if one of these methyl groups shifts over, that gives you this carbocation. This carbocation is actually better than tertiary because it is a resonance stabilized carbocation. And notice how this looks remarkably like the product. And to get the product, we simply use the water that we created here to deprotonate this, or we could use the conjugate base of sulfuric acid to deprotonate that. And we get our product. The way rearrangements work goes back to why tertiary carbocations are more stable than secondaries, and secondaries are more stable than primaries. First example, we had this in the step, where this hydrogen shifted over there, give a tertiary carbocation. Where there was once one hydrogen, now there's two, secondary C+, tertiary C+, tertiary carbocation is much more stable than the secondary carbocation due to hyperconjugation. Essentially, hyperconjugation, we kind of look at this secondary carbocation from the side. Methyl group, hydrogen, there's a carbocation, it's sp2 hybridized. Look at the other. Methyl group, hydrogen. The key is this bond here, this carbon, is sp3 hybridized, meaning what's holding that hydrogen to that carbon is an sp3 orbital. And so what happens is these electrons, what's stabilizing secondary carbocations and tertiary carbocations is hyperconjugation, where these electrons are being shared partly with this p orbital here. But what can also happen is a secondary carbocation can steal all of these electrons, so we can shift this over to there. When that happens, this carbocation, this carbon goes from sp3 to sp2, And this sp2 carbon that was a carbocation goes from sp2 to sp3. Okay? And this tertiary carbocation is like that. Now, this hydrogen can shift back and forth, going from tertiary carbocation to secondary carbocation and back and forth, But the most stable form is the tertiary carbocation, and that is what the nucleophile is going to attack.